Okay.
Right.
It's a pleasure today to have Dr. Aidan from UK. It's a huge impact to our program as a guest speaker. Please, Dr. Aidan, introduce yourself to my faculty member at University of Technology, Iraq. And we are so pleasure. So you are accepting our invitation today. Thank you, and you have the mic.
Thank you very much, Dr. Amjad. I am very honored to accept this invitation and to be able to speak here with everyone today. I can see some faces on the screen. It's nice to see that. So I start by thanking Dr. Amjad, of course, for the opportunity, and Dr. Talib, who helped with the arrangement of this as well. Dr. Talib I met first 10 years ago, and it is 10 years ago since we met, when Dr. Talib came to my laboratory for 1 year. The number of projects went very well, and since then I've had a number of visitors because of that. Talib has published a lot of papers, so it was a very successful 1 year visit, and everything has gone from there. So I'm going to talk about some of the work we've been doing more lately on 3D printing. So if I share my screen, do the entire screen, and we go here and we just hide that. So the title then is Dual Fuel Engine Exhaust Emissions Control Using 3D Printed Heterogeneous Catalysts. And before I say anything, I would like to thank the people who did the work in the lab. So David Shaw was a PhD student who graduated a couple of years ago. Saeed Hajimersi, he was a postdoc for 3.5 years. He's now finished as well. And Callum Davidson is a PhD student who is in his final year, although we expect that to be extended by another year because of the COVID delays. I'm Aidan Doyle. There's my contact details. I'm happy for anybody to get in touch. Please feel free to email me. You're very welcome. So I'm based in Manchester in the UK, and I'm just seeing here that the United Kingdom, it's not so far from Iraq. We're not that far away at all. We're very close together, really. So this is where Manchester is. I come from Ireland, which is a different country, but it's beside the UK, and I've worked here for, well, over 17 years now. Manchester Metropolitan University, it's a new university. It was established in 1970. At the last count, we had 33,000 students. It's one of the largest in the UK. We're the 5th largest in the UK, actually. And the type of work I do, we spoke just before the presentation about zeolites and so on, but I've branched out into other things. And I'm a full professor now, so I've got some responsibilities beyond what I had in the past. So we do 3D printing is a large part of what we do. It's really good, and I would say to you as a group, and I don't know if many of you do 3D printing, it's very good for doing new things because it's a new-ish technique. It looks very good on a grant application. And we have a really advanced 3D printing facility at Manchester Metropolitan University. It's a very, very good thing to do. Low carbon fuels, I've got a lot of money from industry to look at low carbon fuels. That's what we'll be looking at here today, replacing diesel with natural gas. And we have an extensive materials characterization suite. I think you're pretty well equipped as well. We have, XRD, SEM, XRF, BET. We have catalyst testing rigs now, 2 for gas, 1 for liquid. We have an extensive range of facilities. So if anybody is interested in visiting me, spending some time at the university, if we could find some system that works well for everybody, I'm very happy to do it. I mentioned Talib before, and I say it again about Dr. Talib. It was a very successful collaboration. And here we are 10 years later still talking together. So there's a personal friendship part of it too. And it's been a very, very good both personally and professionally. So please feel free to get in touch. Right, presentation outline. So just break it into a few parts, keep it nice and simple. I'll give an introduction to dual fuel engines and exhaust emissions. We'll look at the work we did on developing a catalyst wash coat. Number 3 then is the 3D printed substrates we designed and prepared. Then basically the wash coat was added to the substrates to make 3D printed catalysts. And we also looked a little bit towards the end of the project at full-scale manufacturing to bring this out into the real world. So first part is introduction. So the problem, we all know it, high emissions from heavy-duty diesel engines. So a large machine, truck, as we call it like this, the only real solution is diesel. And I mean, this is not happening anymore because of diesel particulate filters. But, you know, they do put out a lot of emissions, but there's no alternative. You've got to use diesel because it's the only thing will move them. There is legislation. Euro 6, for example, is one of the legislations to control these emissions. And of course, there's fuel cost. So that's the problem. The idea then, to get around this problem, is to substitute diesel with something that's cheaper, less expensive. And I don't want to use all these symbols and so on. This is just liquefied natural gas. And most of what I'm talking about here will be natural gas. So mostly methane substituted into diesel. And these natural gas is cheaper than diesel. It's also, natural gas, if you look at it, it's a clear gas. It's been separated by a natural distillation as it comes out of the ground. So it's already cleaner than certainly crude oil and even diesel. If you do a gas chromatogram analysis of diesel, you get hundreds of compounds, maybe thousands. Natural gas has one, methane, and a few little others. So it's much purer to begin with, and it's much easier to control with the burning. Solution then is to make a catalytic converter more efficient. These are just some examples. We didn't do these are just from the internet. But this is the kind of thing you can do with 3D printing. And we want to develop a new 3D printed substrate and also to look at getting the best wash coats we can for those 3D printed substrates. So these are the standards, European Union standards. These are still in place in the United Kingdom, even though the UK has left the European Union. And Euro 1 was back some years ago, and every few years they bring in a new standard, and the emissions levels are going down. So carbon monoxide, number of grams of CO per kilowatt hour. Kilowatt hour is 1 unit of electricity, so it gives us some indication. So the first Euro standard, 4.5 down to 4, down, down, down. And CO hasn't gone down so much because CO is not a problem. It's very easy to remove CO. So that's not such a problem. Hydrocarbons are a problem. And they've gone down a lot. You can see that the amount of emissions from Euro 5, which was the standard a few years ago, Euro 6 is the present standard. The emissions, you've got to get 70% lower emissions than were allowed at the last Euro. That's quite a big jump for hydrocarbons. For nitrogen oxides, it's 80% lower. So this new standard for hydrocarbons and nitrogen oxides, it's quite strict and it's quite difficult. But that presents an opportunity for research to get around those problems. Particulate matter, this is just the black carbon that develops as a result of incomplete burning in the engine. That has a very low value, but that's actually easy to remove. You just need a filter that doesn't cause too much of a pressure buildup, and that's going to be enough there. So the message here, this shows the different euros and just gives an indication of the allowances as an image, an area. And the message here is that these trucks, nothing else but diesel will do. So you've got to get a solution with a diesel engine. The solution, of course, is dual fuel. So the advantages of dual fuel, I know there's a lot of English words in this presentation, but I've kept as many images and graphs and numbers as I can. I don't speak Arabic, but you all speak English so well, but I'll keep it to a minimum. So some of the advantages, lower carbon emitted because natural gas has more hydrogen than carbon, lower costs, lower emissions of nitrogen oxide. You can use a dual fuel engine with natural gas plus diesel or only 100% diesel. You can switch between the two, and it's compatible with many existing diesel engines. So potential applications are for rail. You can get a railway locomotive with a diesel engine. You can add a natural gas facility. Ships, it's even useful on ships. And, for example, agricultural tractor. So anywhere you've got diesel engine, you can add a dual fuel component, reduce the cost, reduce the emissions, everyone's happy. This is just a similar type diagram looking at rail, ships, power generation for electricity on places which don't have the national electricity grid. On road, then they're the trucks, and off road, so for agriculture or construction or infrastructure or whatever. This looks at the payback period. This is the amount of time needed for the owner of the vehicle to get the money back on what they spent to make it a dual fuel. So rail, 24 to 36 months is typically the time to get the money back from lower running costs. Maritime or sea ships, because they use so much diesel and because the engines are so big, as a proportion, the modification is actually quite cheap, and the saving is so much bigger because they use so much diesel. Anything up to 18 months and you've got your money back there. And the same with power generation on road and off road. So it pays for itself. And for companies, especially ones where margins are tight, it's a very big advantage to use dual fuel to cut costs. Global truck production. There's a little bit old, this diagram, but trucks aren't going away. You're going to need lorries to transport goods. The United States, for example, they use more trains than trucks lately, but even that, they're all on diesel. So the natural gas conversion is still favorable there. So we see for 2014, the last year I can get numbers, natural gas only made up 2% of the fuel used for trucks. So that can go up to 40% maximum substitution. So there's a huge growth market there to increase the natural gas usage in these diesel engines. So a four-stroke engine, I'm speaking to an engineering group. I'm an industrial chemist with some chemical engineering background, but I'm predominantly a scientist, so you'll know more about this than I do. And it's very well known. 4 strokes. First stroke is where the valve opens, air comes in. Second stroke, going back up, air is compressed with the valves closed, temperature increases. Third stroke, the high temperature in there is sufficient to ignite diesel when it is injected. And the last stroke then, the third stroke, that pushes down the piston. Piston goes back up, valve opens, exhaust goes out. Classic 4-stroke diesel engine has been around for more than 100 years. When the dual fuel engine works, natural gas is introduced to the air going in at the inlet manifold. That flows in to the chamber and it gets compressed with the compression cycle. With natural gas, like hydrogen, we're starting to work with hydrogen. Both natural gas and hydrogen have a very high auto-ignition temperature. So the compression alone and the temperature and heat raised from the compression is not sufficient to ignite the natural gas or hydrogen. But it is sufficient, as we know, to ignite the diesel fuel. So once diesel is injected and the flame comes and the heat is given out, the natural gas combusts and it adds to the explosion, really, pushes the piston down and the exhaust gas comes out. The trouble with natural gas, while it is a very clean, cheap fuel, the tetrahedral arrangement of the carbon with the 4 hydrogen atoms attached to it, I mean, it's a bit like a diamond structure. It's very stable, or it's a bit like quartz, where you have silicon dioxide. This tetrahedral arrangement is very, very stable. So not all the natural gas burns. It's not so bad, but it doesn't burn as much as the diesel. And you get a quantity of natural gas. Most of it is burned, but some of it comes out, and it just happens to be enough to be above the Euro 6 limit. And we were approached to solve this problem for a company in the UK who want to solve their emissions problems to sell more natural gas engines. So the after treatment system for heavy duty vehicles, they're all pretty much the same, and they are much more complicated than they were. I mean, 20, 30 years ago, you had one catalytic converter. It tried to do everything, didn't do it very well. Now the conditions are much stricter. You've got to have a number of different converters and parts. So the first part is oxidation. The air inlet into an engine is quite high now compared to what it was. So it gives very lean conditions to burn the fuel completely. That's why engines are more efficient than they were. But then that means you have a high concentration of oxygen. That's fine. Diesel oxidation catalysts work quite well, no problem there. The diesel particulate filter then, that takes anything like soot and so on that doesn't burn over the diesel oxidation catalyst out. But because there's so much oxygen in there, you've got to add something to reduce the nitrogen oxides. And that's done, the most common one used at the moment, the industry standard, is urea. That is sufficient then to reduce the nitrogen oxides to nitrogen and water. But then you make ammonia in the process, and you've got to oxidize ammonia. So you have an oxidation, physical, filtration, really, a particulate filter, a reduction, and another oxidation. They tend to be quite big. So when you're designing catalytic converters, anything that can make the catalytic converter smaller or more efficient for the same size, because there's such a limitation on space in modern engines, will be very, very valuable. So let's just keep that in mind. The basic unit is a monolith made from ceramic, and you place, so this is before wash coat. The wash coat is just a catalyst. The wash coat means it's just placed on the underlying support, and you can see a bit of the wash coat active catalyst here. And this is a cross section, so you've got the monolith substrate, that's the first one, and you've got some kind of porous support catalyst over that support. Alumina is used quite a lot. We use zeolite as well, but zeolite is not so good with water over the long term. Even though it's more active immediately, alumina is known to be much more stable and much more active over the long term. And you just place your metal nanoparticles, disperse those on the surface. They're what cause the actual catalysis to occur. Okay, we have in the last few years designed and assembled 2 catalyst testing facilities. This is one of those. This is the more complicated one, so I'll show you this one. And if you're familiar with these, that's fine. I won't take long to do this. But you can think of this as being like an exhaust emissions from an engine. And there's really 3 parts. Let's simplify it. It's very difficult to design this, right? I mean, it's easy to explain it, but this took us a long time to design. But we can simplify it. You've got a series of gases coming in. You've got a series of mass flow controllers. They all join together, so you can choose whichever gases or series of gases you want. You can also vaporize what are liquids at ambient temperature to get those in there. So one of the materials we worked on lately was isooctane as a model compound for gasoline. And that's fine. So you can get those. We usually use helium as a carrier gas, oxygen as the oxidant, and methane. We use pure methane as a model for natural gas. But if it works, if you can break down methane, everything else will break down. So that's one part. That's like the gases coming out from the engine. The second part then is the catalytic converter. And that's just the furnace. So you've got your gases coming out here, the common line. Let's just ignore what's below there for a second. It's not really relevant to this project. Gases come along here, and they flow through a solid catalyst and flow on to be detected by our analyzer, which is GCMS, and we have TCD and FID in there as well. It's a really good system. So start off your reaction, flow the gas around the catalytic converter. You get a signal for what goes into the catalytic converter. Switch these 2 valves, flow through the catalytic converter, you get a signal for what comes out. The difference between the 2 is a measure of how effective your catalyst is. And you test one catalyst. If it's good, you find out why, and you do another catalyst with that and try to make it better and better and better, and so on. And we spend a lot of time doing that. That's just an image of the rig. That's in our fuel cell center. So it was very good to get the funding, because we got the funding for the instrument from the fuel cell center, and we do some work on hydrogen. So, a lot of things going on behind there. That's the gas mixing. That's the side of the furnace. That's the GCMS. Works really well, automated. It's a brilliant system. So the first reaction we looked at, and we didn't really spend much time at this because methane was the focus, but we said we would do it for the company just to start off. It's CO oxidation, and we're looking at conversion of CO versus reaction temperature in the furnace. And, so we want a high conversion. 100% conversion means all the CO is gone. And really, you want that conversion being as low temperature as possible, within reason. So we looked at a lot of different catalysts. So the first signal is no catalyst. You do get some reactivity, but of course it's not as much as the catalyst. And then we just looked at different supports, different metals, different combinations. HAP is hydroxyapatite. This is platinum metal on Y zeolite in H+ form. Platinum on hydroxyapatite. We have another method of making catalyst, magnetron sputtering. It's makes it from a plasma, so the catalysts tend to be very well dispersed. And then we looked at different things like gold, which is known for CO oxidation, ceria, which is an oxygen store, titania, and there's alumina, and various combinations thereof. This dashed line, 300 degrees, the temperature at which gases come out of a dual fuel engine are about 300 degrees or a little bit more. So if we can get a catalyst that works below 300 degrees, that's very good because you don't have to supply any heat. So we just keep that in mind. So there's a series of catalysts, most of which work for CO. We've fixed the problem for CO. It was always going to be easier than methane, but it's fixed. Methane oxidation then, same again. So we look at methane conversion on the left, on the y-axis rather, temperature in degrees C on the x-axis, and again a series of catalysts just to see, you know, we were setting up the catalyst testing rig and we had a new student learning how to make catalysts and all that, and you can see a big variation. So again, same catalyst actually. I know we've put in gold here. Gold is not much good for methane. It doesn't activate methane, or if it does, it doesn't do it nearly as well as platinum group metals. But we had the catalyst present, so we just tested them anyway. And yeah, we get a good indication there of what's working and what's not. And we're getting some that are quite active below this temperature range from the natural temperature of the gases. We don't have to be below here, but it really, really helps if we can. And it's good that we have some catalyst below here. It was encouraging that we could have a system that would be successful, and it has been. Then we looked in more detail at different parameters, and I'm not showing all the results here. We don't have time, but I'll give you a good flavor of what's going on. So this is just looking at different zeolite supports, ZSM5, Mordenite, HY, and we find HY always works best. I mean, it's just a phlogisite structure. It seems to work best. Of course, it's the metals on them that are doing most of the work, but zeolite Y, it doesn't have the very small pores of ZSM5. It has a high surface area. We know it well. So we tend to use zeolite Y because of that. And then on zeolite Y or HY, we wanted to look at optimizing the metal content. And again, I mean, you can spend years doing these catalysts and different variations. We didn't want to do too much work on it because we wanted to focus on the 3D printing of the substrate. So we just chose two metals, palladium and platinum, both of which we know are active to break up methane. Palladium is more active, but less stable. Platinum, less active, but it stays active for longer. So both together tend to work quite well. And we just use, you know, 0.5 palladium for 1 platinum, 1:1, 2:1, 10:1, and so on. And we saw that the optimum was, you know, 1:1 is what we found, or it didn't make much difference once you go above 1:1. Well, 1 palladium, 1 platinum, we found the best, and we used that. Next was to optimize the metal content. And remember, this is an industrial project. They need to be aware of costs. So we needed to look at that. 2% PGM is just platinum group metals. So this is just platinum plus palladium 1:1. We have to use this PGM because that's what the industry guys always talk about. 2%, fine, it works. 4% is much better. But really, once you get beyond that, then 6% is better, 8%, 13%, not much improvement once you go beyond 4%. So about 5% there is enough not to be wasting it and to get the full amount thereof. Just a selection of some of the catalysts we looked at, just some catalyst characterization. XRD, so this is the catalyst we used. You'll see in a few minutes we used a large catalytic converter that we could only make once. We only had, because of time and cost and so on, we only had one shot to get this right. So we made a mixture of different supports to get as much information from the single recipe that we could do. So zeolite, alumina, ceria, zirconia, we're well used to those, and we get all the characteristic peaks both before and after impregnation of the metals. And there's really not much difference. The structure stays intact and so on. There's small differences, but nothing that means anything. TEM, this is our catalyst. You can see the metal nanoparticles on the surface, the dark parts. Before reaction, fresh catalyst. And we looked after 90 hours reaction. And now you're never going to get the same particles with TEM. You just can't find the same thing in two separate samples. Even the same sample analyzed twice, the probability is just nearly zero. But you can certainly see that the dispersion here I think if you average it, is no worse than the dispersion here. That is, the catalyst is stable, and that tallies with the catalyst testing results. We also did porous symmetry, nitrogen adsorption, and the BET surface area then of this catalyst, this average, if you like, of all the different supports, 363 meters square per gram. That's a decent, good surface area. Right, 3D printing then. We looked at, well, 3D printing. This is stereolithography. This has worked very well. And, you know, as I said before, I would consider getting some 3D printers. They're much cheaper now than they were. You can get them for a few £100s. They introduce novelty and so on. I'm happy to advise on that. So that's your 3D printer. It prints in 2 dimensions and then goes up, prints in another 2 dimensions, goes up and so on. So it's 3D, but it only prints 2-dimensionally at any time. This second one, we never got to use this, but it's something we're looking at now. This is a Microlattice Ceramic, it's called. It has a series of these masks, which are part of which let the light through and part of which block light going through. So if you have a liquid monomer that polymerizes under UV light, if you arrange these masks in the correct way, and you can use a number of masks, you use, you know, not just one, then with a single beam of UV light, you can form a 3-dimensional structure in here with porosity. It's quicker than 3D printing because everything happens at the same time, and it's something we'd like to look at. The other method then, and really this is what we're competing with, so this is like the industry standard. You push a ceramic in 1 dimension, just chop it off here, and you get a series of these monoliths, and the idea then was to rotate each monolith above each other, and we get a catalytic converter like that. That isn't 3D printing. It's okay, it's quick and it's cheap, but it's not as good as the 3D printed substrate because we get a greater number of turns. We're turning maybe every, you know, millimeter, where this one is turning, you might have to go 10 centimeters or something like that to make it stable. So each one has the advantages and disadvantages. We've concentrated most on 3D printing. So the next thing then is to come up with structures. Now, if you want something to work well for a company, they need to know, well, it really needs to be simple. It needs to work very well, but it needs to be made as simple as possible, giving something that is complex. So we spent a lot of time thinking about this, and really the way we've made this, we print straight lines. So there's one, then we print another straight line, print another straight line, another straight line, and the next thing then is to print a circle around it. I can't show the whole thing because I want to compare some different angles. And then you go up 1 layer and you print it again, but this time you print at an angle. So you print at 30 degrees to the one below, 30 degrees to the one below, and so on. And with just one change, 30-degree change on each line, which if you think about it, requires 6 different prints going up before it reaches 180 degrees. And because it's symmetrical structure, that's all the instruction it needs to print, and you just let it go until you reach the top. Very, very simple for programming, and this in computer-aided design, and that's just with a simple 30-degree turn at each step. This is a 90-degree turn, and that's what you'd expect. I mean, this is a much more open structure than the 30, but again, think about it, you get all this surface area, look. Every single line that's printed, you get a surface. Compared to, for example, this is the commercial standard, CPSI. Here we have another confusion, but this is cells per square inch. So this material here has 400 of these cells per square inch in 1 square inch. And you see, you don't have the same surface area on this. This is just a flat surface all the way down. It's still a decent surface, but it can't be as high a surface area as this. So the 90-degree that we print is not the same as the industrial standard at all. And then you have a 60-degree. And interestingly, the 60-degree and 30-degree are not the same as each other at all. They give completely different prints, even though you might think one is, you know, they're the same from 90. It doesn't work like that. Anyway, they're the prints. We use computational fluid dynamics. Now, I'm not an expert in this, but we learned enough. My postdoc did most of this, right? And we got some help from a member of staff from the mechanical engineering department here. But this was very helpful. Before we printed these, we investigated the designs for turbulence and for temperature. So really what we want is turbulence. If you think about it, think of a molecule of gas going into this structure. It's got an open channel here. It can just go all the way through to the other one and maybe not react so much. A molecule of exhaust gas goes in here. It can't go all the way through. It has to hit a surface. Then it hits another surface, and so on. So a complicated structure that's 3D printed should, in principle, increase the turbulence and mass transfer of reactants going through it. And ideally, what we'd hope to see then is an increase in reaction conversion to bring down the emissions to below the legislative limits. So we look at that. The top one is temperature profile during startup, and the bottom one is turbulent kinetic energy. And we compared a 3D printed structure on the left with the commercial structure on the right. And you can see at a glance, so this is after starting up, running for a while, what the temperature will be of that just by the gas flowing through. We couldn't model in CFD any chemical reaction. There is another program to do that. So this is just the fluid alone causing this temperature increase. Of course, if there was a reaction going on, it will be enhanced. But that's not what's important. The important thing is the difference between the two. And you can see the temperature is going to be higher where you have the 3D printed structure because of the additional turbulence causing that temperature increase. And for a real life system where an engine starts up as being cold, the catalytic converter is cold, the quicker it heats up, the quicker it can become active and do its catalysis. Looking at turbulent kinetic energy, this is a measure of the turbulence. And again, I'm not an expert. I'm sure there are some experts in the audience on CFD. Turbulence is quite a difficult thing. It's very useful, of course. Really, really good to know this. So I'll, submit to the experts on this. But again, we learned enough and knew enough to be able to tell the difference between the kinetic energy for the 3D printed structure, which, based on the colors alone, is higher, quite a lot higher, than the structure from the commercial structure. Okay, so CFD shows us then that these structures are having the desired effect, and the next thing we said was we'd print them. So we started printing. Here we go. Printing was very difficult, much, much more difficult than we expected. That's not a reason not to do it, but it's just something we found out. If you print something like plastic is very easy because you've got one material and it stays together. It either all melts or it doesn't melt. It all goes one way or another. With the ceramic, we printed cordierite, but you could just as well do zeolite or aluminum. We've done those since, but we started with cordierite. It's a suspension. It's a solid in a liquid, and it's just more difficult to print. I mean, the solid can come out quicker, the liquid can come out quicker, the mix changes, and we learned all this stuff slowly, but we got there. These are the designs, so you can see this layered rotation as you go up and so on. This is what we call the log cabin effect. It's not another diagram. Now, these don't look good, I accept that, but these were our first prints with cordierite. We printed much better in plastic the first time, but these were okay. These were enough for us to print. They stayed together, they were stable, and we were able to do some analysis on them. So again, just comparing the results you'd expect between the 3D printed and the straight structure. So then we looked at them in the reaction, methane conversion on the y-axis, temperature on the x, and they're the conditions. They're all the same, except for the substrate. Everything is almost the same. We got the wash code as close as we could. They're all very close to 0.25. These monoliths are 2 centimeters by 2 centimeters. Feed flow is 50 ml per minute, and again, stoichiometric conditions, twice as much oxygen as methane. That's a 2-to-1 reaction, so it's exactly what's required. And you can see this is the commercial standard. These are the 3D printed substrates. All the 3D printed substrates are much better, significantly better than the commercial standard. And bear in mind, we're limited to 50 mils per minute. I'm not so sure the turbulence was that strong because it's just because our catalyst testing rig is limited to 50 mils per minute. I think if we had a stronger flow, then you might see more turbulence coming in and a bigger difference, but I'm only speculating. But that was a really good result. That validated the whole process and showed that 3D printing really, really increases significantly, massively, the conversion of these materials. Again, I don't know how much turbulence explains this. What can explain it is if we look at the surface area of the 3D printed, because there's the way the material is oriented, you got loads more surface. So the CPSI 400 with the flat channels, 3.56 meters squared per liter of catalytic converter. All the 3D printed structures are above 10. So you have a bigger surface, and not only do you get possibly some turbulence, but you also have a bigger surface, so you might get the wash coat dispersed better. In any case, it's a much better catalyst, and 3D printing works. And they're the prints that we did. We went then, the fifth part and the last part of the talk then is full-scale manufacturing. This was the first printer we bought. It's fine, we still use it. Now, we bought that about 4 years ago, and I think you pay much less for it now. These are very good printers, but it was quite expensive when we bought it. This is a 10 centimeter wide print. That was very difficult to do at the start, but now we can do those quite easily. This is, I have no scale bar. I should have put in a scale bar now and just seen. This is 10.5 inches. So what's 10.5 inches? 10 by 2.5, 25, about 26 roughly centimeters wide. And actually, this is before it was cured in the oven. So it would nearly be 30 centimeters to allow for shrinkage. This took us days to prepare. And we had to put on a catalyst on this. It was quite expensive. So we only made one. Sorry, we made two. This is the full one we made. Yeah, we did make two. And the other one then we made was, because it was so difficult to prepare a full one, we just made 4 quadrants and put them together. But it worked. And it's not been done before. This is completely new. And while it was a lot of work, it worked out really well. So the fact that we can make a full-scale catalytic converter meant that we could test it in a commercial test facility. The company paid for this. This is about 40 kilometers away in a town called Preston, just north of Manchester. And it's, so this is the kind of thing you get with your car. Every year in the UK, you've got to get your car tested for the exhaust emissions, and it goes in or whatever. So they have a dual fuel test facility. This is the installation. This is the gas analyzer. And they've got various variations as to what they want to do. So, you know, they got this bypass and all like that. It's a really good test facility. It's expensive, but we got access to it, and it really was good. These are the 4 quadrants put together. So this is the canning setup, and you can see here, this is just to hold it in place. You got some kind of wool, obviously not a carbon-based wool, some inorganic wool, encased in a can like so, and just the direction of flow. And now we didn't do as much work with the large one, but this shows the 3D printed substrate on the left, the commercial substrate on the right, and we're looking here at the methane emissions coming from out of the exhaust. So this is after the catalytic converter, as a function of 2 different things. One is the load on the engine. So you can force the engine to work harder. So 100% is the engine working as hard as possible. You use a voltage with a dynamometer to put a load on the engine as if it's starting off going up a hill as a model, and reduced thereafter. So different loads, and also different amounts of substitution of natural gas. So 20% natural gas at different loads, 30% natural gas, 70% diesel obviously, 40% natural gas, and so on. I mean, at a glance, the 3D printed substrate looks a little bit lower, but it's not much. But it's roughly the same. It's this shows that a 3D printed substrate can compete with a commercial substrate and give the same kind of emissions. Now, we made this about 3 years ago. If we were to make this now, we would definitely have lower emissions. We can make much better catalysts now. We can make much thinner walls for the catalytic converter. Where this is CPSI 400, we can make this higher. I'm speculating, of course, but I think we could have a much better catalytic converter now if we were to do that. So there. So in summary then, and conclusions, the catalyst wash coat, we made a good one that decomposes methane at low temperature. We designed and assembled a new catalyst testing facility. We actually did 2 of them. The other one is not so complicated as this one, but it works just the same as GC. And they are the first 2 catalyst testing facilities at Manchester Metropolitan University, and they get used all the time. That was a big deal. we designed and printed 3D oriented channels within a catalyst substrate, and we also got to use those at full scale on a catalytic converter under realistic conditions, and that material held together very well. It was structurally stable. In fact, we tried to analyze some of the metals by TEM after being used in the facility, and we had to break it with a hammer. So it's really, really stable, worked really well, and the project worked really well overall. So thanks again for the invitation, and thank you for allowing me to speak. Thank you all very much.
Thank you very much, Dr. Aidan. I'm going to abuse my power as a director for this lecture to ask you first.
Yeah.
Actually, I have a question. I will start with, there is no mention for regeneration step or process for this kind of prototype.
To regenerate what, the catalyst?
There's a lifetime. What is the lifetime for this kind of project?
Yeah, we didn't get to do, I mean, we did some stability testing. We did 90 hours. I couldn't show all the results here. We looked at 90 hours continuous testing in the presence of water vapor, and the catalysts we made were stable. We haven't had time to do proper lifetime testing, and in the lifetime of the project, I mean, it took us nearly a year to just build the rig. It's an ongoing project. We haven't done as much lifetime testing or regeneration as we want. We've also avoided sulfur. I don't know if you noticed that or not. There's only so much we can do at the moment. The company have a project where they're looking at those things, but we haven't had time to do those. It would be interesting though to see.
Yeah, for sure, because there is an expectation for the temperature for the regeneration, this type of prototype. Any expectation for the temperature needed to regenerate it? Because it's important to know. Yeah.
The biggest problem is sulfur. I met with the company before lockdown, before COVID-19, because they haven't been doing much since. They had a system that I was working on where the catalyst runs for a few hours. The sulfur builds up on the catalyst. There's no way to get it around it. And then what they do is they heat the catalyst artificially in the presence of oxygen, burn off the sulfur, regenerate it that way, and then go for a few more hours again. That was the